Researchers Laurent Bigot and Espen Andersen, working at the Ersika Institute in Lille, France, are expecting to reach petabit per second data transfer rates using new generation optical fibers. With the potential to transmit 7 times more data in the same space, these multi-core fibers could be the answer to the impending data capacity crunch.
There is a need to increase the capacity of the present fiber that are used in the telecom networks. This is called the capacity crunch. It means that in few years, the need from the user will reach the real capacity of the fibers that are installed undersea, for example. And here at the Institute, we are working on new generation on optical fibers that will be able to face this capacity crunch. So the main interest in such a fiber is that it has the possibility to transmit the same capacity as several single-mode fiber, but in the same piece of glass. The maximum capacity of single-mode fiber cables is about 100 terabit per second. With our solution, we expect to reach the petabit per second capacity, and then more than this, I hope that we will also be able to propose some solution that can save energy, reach the same level of capacity at a lower cost for the environment. At first, we are more specialists on the optical side because we are manufacturing the fiber and we test them for their optical properties. But since about 3 years, we have been working on data transmission on optical fiber. So when we decided to invest in an equipment dedicated to test the data transmission, it was important for us to have a full solution, user-friendly, for us that were not so familiar with data transmission and data manipulations. So that's why we have chosen the Tektronix solution, because it includes both the generation of the data patterns and then after the optical transmitter, and the possibility to detect all the signals and then analyze.
One of the challenges that we face when we are working on multimodal telecommunications is that whereas in standard single-mode fibers, you only have 2 degenerate states, which you have to disentangle in the signal treatment. In multimodal fibers, we have at least 4 degenerate states, and we now have to disentangle 4 times as many states in the signal treatment. And for the experiments, we have been able to use the Tektronix equipment, which allows us to synchronize 4 oscilloscopes, which allows us to measure these 4 degenerate states at the same time.
Here we have an example of data transmission over a multi-core fiber. It is a piece of fiber in which we have 7 cores, and we have the possibility to send data streams in each of these different cores. So with the experiment we have here, we have a transmitter, and we send data information in the different cores of our 2 kilometers long fibers. And here we can analyze the data that is transmitted and the quality of the transmission. So in this particular example of experiment, we have the proof that it is possible to transmit about 100 gigabit per second in each core without degradation of the signal due to crosstalk, because of the specific design we applied to the fiber. And with the equipment, we have the possibility to demonstrate that such a fiber is available for a short-range link, for example, as the one that is needed for a data center. Using this technology that is called spatial division multiplexing, it's possible to adapt it to different contexts for short range, like the multi-core fibers, but we also are working on the application for long-haul transmission. And in this case, the idea is to save energy.
What I like about multimode fibers is that at first view, they look random, because if you send light into a multimode fiber, what you get out of it doesn't in any way resemble what you put in. But if you look closely at the multimode fiber, it's actually a deterministic object. And if we are able to measure this deterministic behavior of the multimode fiber, we can use it in a large range of applications. So the Tektronix equipment allows us to measure the output of a multimode fiber with a high precision, which allows us to basically unscramble the random behavior of the fiber in post-processing.
What I love in the research activities I'm developing here in the lab is that it is application-oriented research, meaning that we are doing, from a certain point of view, pure research by investigating how light is propagating in a spatial fiber. But we know at the end why the fiber will be used for.
I see my job as a researcher, as someone who has to try out new solutions that haven't been tried before.
With our research, we hope to be able to delay what I called before the capacity crunch in order to provide for everyone a better internet for the coming future.